Hello everyone. Today we are going to discuss problems again, just like in our previous lecture. And the problem that we are going to consider is something like this. So again we have a cantilever beam like that, and we have a wall here. This beam is attached to this wall, and for the load we have a uniformly distributed load on the top of this beam. We represent it through this set of arrows. So even though all these arrows are not perfectly vertical, please assume that they are so. Okay. Now what we say is that the magnitude of this uniformly distributed load, it is given by this W, but please note that W is not Newton, rather it is Newton per meter. Okay. Now the question is, what is the deflection at this free end? Okay, so that's the question. What is the deflection at the free end? That is at this end. Now, if we wish to apply Castigliano's theorem on deflections, we know that we need to have a point force at the point where we want to find out the deflection. But here you note that we only have a uniformly distributed load. There is no point force acting at this end. So what can we do? So there is a little trick involved here. It is called the method of fictitious force. So since we do not have a point force at this end, we artificially introduce a point force. Okay, so we just introduce a point force here like this. Okay, we say its magnitude is P. We do all the processes as if this were a real point force, not an artificially introduced one, and just at the end we set things back to as it were at the beginning, as it was in the beginning, by setting this P equal to 0. Okay, so that's the trick. Okay, so to introduce a fictitious point force at the free end, and proceed as usual. So if we want to proceed as usual, what we'll do is we'll take a cut section at a certain distance from this free end, and we'll say that we are going to take our origin here at this free end and take the x-axis oriented like this. Okay, so if we just consider the free body diagram of that part of the cross section, to the right of this cut section rather. So what we'll have is this thing, where this point force, sorry about that, this point force is very much present, and we also have this uniformly distributed load. Of course, only the part that is under concern. All right. and please note that this is still W of W intensity. Okay, now at this exposed section, what we are going to have is sorry about that. Is a moment and a shear force. Okay, now what we are going to do is exactly the same as we had been doing in the previous lecture. So we wish to find out this M. Okay, so this is the M which appears in the formula for where we use Castigliano's theorem of deflections. So this M, let's write the equation for it. So this M is in the clockwise sense, and the moment contributed by this force P about an axis which is passing through this end is going to be P times X, that's the magnitude, and its sense is in the same sense as this M, so it is plus Px. Note that this uniformly distributed load is also going to exert a moment or contribute a moment when we consider its contributions about an axis which is also passing through this end, and that will be given by this expression Wx. So Wx accounts for the entire force which is acting, and since this is a uniformly distributed load, we may think of it to be acting effectively at a distance at the midpoint of this section, Wx into x by 2. Okay, now I would encourage you to think that if this were not uniformly distributed, rather like some arbitrary distributed load, then how could we arrive or what kind of a method we could use. So what we basically have to do is we have to take a little element here. I think we discussed such a method back in our course of applied elasticity. Nonetheless, I would encourage all of you to think about what we could do if this were not uniformly distributed. Okay, so with this we can find out this expression of M, which is just minus Px minus Wx square by 2, and now we wish to find out the deflection at the free end. Let that be represented by this d. D is going to be equal to 0 to L, and today we are going to use that this version of the formula. So we had discussed this particular form in the previous lecture. Okay, so we basically have del P of integration 0 to L m square by EI, and if we actually carry out the differentiation, so it becomes that m square, from that we obtain this m by EI, then del m del P. Okay, I hope none of you have a problem with this. So the important thing to note, however, in this problem is that this entire calculation has to be done in such a way that its value is evaluated, this entire value of the integration, it is evaluated for p equal to 0. Okay, that we must remember. So let us quickly carry out the calculation here. So we have for m this minus Px minus W x squared by 2 divided by EI, and then del m del P, that is nothing but minus x. Okay, so from this expression we have this dx 0 to L, and this entire thing, let us not forget, must be evaluated at p equal to 0. So since there is we only have to deal with the algebra here, you note that we might as well set p equal to 0 right away here. So all that will be left with is this 0 to L W x cube by twice EI dx. So what we are going to end up with is W L4 L to the power 4 divide by 4, but we already have a 2 here, so this is 8 EI. Okay, so that's the answer. That's it. Okay, so exactly following the method which we had been using earlier, but only utilizing this fictitious point force, we have managed to find out the deflection, even though there was no point force to begin with. Okay, and this is the method which we'll follow all along, that whenever we are asked to find out a deflection or any other entity, as we'll see, like slope, at a point where the force is not present, where the point force is not present, we'll artificially introduce the point force and then proceed, and then finally we'll set that artificially introduced point force to be equal to 0. Okay, all right, so we go on to the next problem now. So in this problem, we are going to discuss something which is counterpart of the deflection. As I just mentioned, it is the slope. So we are interested in finding out the slopes. Now, directly in our statement of the Castigliano's theorem of deflections, we have not talked about slopes, about finding the slopes. We have only talked about finding the deflection at a point where a point force is being applied in the direction of the point force. So before going to this problem, let me just discuss very briefly a corollary to the Castigliano's theorem of deflection. Okay, so this will be without any proof, but I'm sure that many of you who may have studied energy methods in their undergraduate days would be familiar with what I'm going to say. So, corollary to Castigliano's theorem of deflection on deflections. So just like we have D, or let's say U F bar is equal to del U dash del F. So this was exactly Castigliano's theorem on deflections. We will have for slope we have for slope theta. So this theta denotes the slope. Okay, let me write this as m naught to represent it, to highlight the fact that this m naught is actually the applied external moment. Okay, or an applied couple. Now, as before, for Hookean materials, we can directly use the strain energy instead of the complementary energy. Okay. And we state all of this without proof. Okay. Now, especially for beam problems, we have this UF bar that is like del F of this m square by twice EI dx 0 to L. We have seen that, and that turns out to be equal to 0 to L m by EI del m del F dx. So just like that, we will have for the slope so the expression for the strain energy, as it is dependent on the bending or the flexure, this part, so this is the, you understand that this entire thing is the strain energy, that doesn't change. Okay, it is only with what with respect to what we are differentiating, that changes when we have to find out the slope. So just like before, what we'll have is this formula. All right, so let us illustrate this with an example. Okay, so in this example, what we are going to do is we are going to use this thing certainly, but at the same time we are also going to utilize the concept which we had introduced with regards to the fictitious force in the previous problem. Okay, so it will be, in one problem we are going to apply two different concepts, the concepts of the fictitious force, or equivalent to the fictitious couple, as well as this thing, this slope formula. Okay, so the problem is like this. We again have a cantilever beam like that. This is the wall to which it is attached. And this time there is a point force, but it is acting at a certain distance from this end. At a certain distance A, let's say this distance is A from the so from the right end, and the magnitude here is P. Okay, let me rewrite that better. Okay, the question is, what is the rotation of the free end, rotation of the slope of the free end? Okay, so that's our question. So as before, we note that at this free end we certainly don't have a point force, but for the purpose of our rotation or slope, we don't need that. What we actually need is a moment, but that also we don't have. So since we don't have that, we artificially introduce it. So let's say we introduce this. This moment m naught, with the intention that after all our calculations are done, we are going to set this m naught equal to 0. Okay, so we are going to take this again, as before, we are going to take a cut section. Okay, and we note that just like before, we are going to take our x-axis from the right end like this. Now we're going to write down the expression for the moment. So you see, there is a certain algorithmic systematicness to the way that we proceed with these problems. Okay, once you do a few problems, you'll also get the hang of it. Okay, so after you've taken the cut section, we basically consider this. Let me do it a little bit more systematically. We consider this cut section on the portion of the beam to the right of this cut section. Sorry about that. Okay, we have this m naught here. We also have this this p here, and at this end we need to complete the free body diagram by writing this m and this shear force P. Okay, and now we are going to write down the expression for the m. So this m is in the clockwise sense, and you note that this m naught is also in the clockwise sense, so they have the same sign. For the contribution of this P towards the moment about an axis, calculated about an axis which is passing through this end, we note that we have to use the heaviside or the step function here. Okay, so it's like this, that the moment arm is given by x minus a, because you understand that this entire thing, so this entire portion is x here. Okay, this part is a, so the moment arm is given by x minus a, this distance, but that gets activated only when you are at a distance x which is greater than a, and that fact is captured by writing this or multiplying this term with this heaviside. Okay, so this entire thing is equal to 0. Now yesterday, I have actually recorded the previous video yesterday, so I said yesterday, but in the previous video we had proceeded after writing something like this using the Macaulay bracket and then going to symbolic Python to do our calculations, but you see, for simple enough situations we can actually proceed by hand, which is what I'm going to show here. Okay, so just to make the thing nice and explicit, we write the actual expression for m. Okay, so this thing, so this h is the heaviside. Okay, now we wish to find out the slope. Okay, so for that we use the formula which we had written in the previous page. Now this m is this entire thing that we can write this ei remains as it is. Now for the del m naught, you note that it is only this term which is going to contribute. Okay, so that's actually good news for us because it makes the expression very simple. All right, now you note that this integration actually goes from 0 to L, so it is going from this part to this end. But due to the presence of this heaviside, we need to break this integration term by term. That will actually make our life a bit easier. So for the first one, okay, and please note that this entire thing has to be calculated at m naught equal to 0. Okay, similarly here this entire thing has to be evaluated at m naught equal to 0. Now before going on to the next step, let me just note that within this entire integrand, you see, I am very much free to immediately set, before going into the next step, this m naught equal to 0. So that will make the calculation much easier. So what I'll do is I'll do this multiplication with this minus 1. So I'll have this p into x minus a. But now I'll already activate this heavy side so that this integration from 0 to L actually gets converted from A to L, because whatever was from 0 to A, that becomes 0, because h or the heavy side of x minus a, as long as x is less than a, that is equal to 0. Okay. So now it's quite simple enough. All that I have to do is finish up our integration here. So this is a to L. This is actually I can carry out the integrations. So this becomes x square by 2 minus ax, putting the limits of integration. Okay, so I'll skip a couple of steps here and write the final form here. This is p by is ei. So please note that I actually know this answer, which is why I'm able to write it down in one shot. I have not actually done the intermediate steps in my head. Okay, so please do not overestimate my abilities on that regard. All these things I always do step by step, but just here in the interest of time, I'm skipping ahead. All right, so this is our answer. And you note that if you have the special case of a is equal to L by 2, you'll get some familiar formulas which you may have come across during your gate preparation. Okay, so on that note, we have learned two important concepts here. One regarding the introduction of fictitious forces or couples, and the other regarding the use of the corollary to Castigliano's theorem on deflections, such as to say that it is something like the Castigliano's theorem on slopes using the moment. Okay, so on that note, I'll end this lecture and we'll continue with problems in our next lecture. Thank you very much.